Hello everyone, I'm Yuanjie Li from Tsinghua University. In this talk, I'm going to use DDoS as an example to show how to fight against network attacks that we don't know. Network security is an asymmetric war between attackers and defenders. The evolution of security defenses almost always lag behind the emergence of new threats. It's usually too late to come up with remedies before new threats have already caused negative impacts. This phenomenon is exhibited by recent advances in adversarial learning, or so-called deepfake, which empowers criminals to refine their attack strategies. So, it's open to question if defenders still have decent chances to win this race against intelligent attackers. In this paper, we studied this question in one of the most serious threats to the internet, distributed denial of service, or DDoS. In DDoS attacks, attackers disrupt victim services by exhausting their network resource with compromised botnets. In the past decades, we have seen numerous DDoS attacks to many institutes such as Google, GitHub, and Amazon, with more than 1 terabyte per second malicious traffic and huge financial loss. As a result, DDoS is probably one of the most studied topics in network security. If you do a Google Scholar search, you will find tens of thousands of papers about DDoS. The publication list goes longer and longer. Numerous DDoS defenses have been proposed, such as ingress filtering, source address validation, anomaly detection, anycast, traceback, internet architecture change, and many more. As for commercial products, huge scrubbing centers have been widely deployed to absorb the global DDoS traffic. On the other hand, despite these extensive excellent efforts, the frequency and intensity of DDoS still continues to grow without any signs of stopping. So, we have to ask, why is DDoS hard to eliminate? What does intelligent unknown DDoS imply for mitigations? And how to fight against intelligent unknown DDoS? Let's look at the first question. Why is DDoS hard to eliminate? It's because attackers and defenders are asymmetric in at least 3 aspects. Number 1, it's much easier to get attack capacity than defense capacity. Attackers can hijack numerous hosts to form huge botnets at low costs. Instead, the defense capacity is usually expensive. For example, to defend 600 Gbps DDoS, we have to pay $150,000 per year for the scrubbing centers. Number 2, the attack surface is always larger than defense coverage. Attackers can easily discover and exploit new vulnerabilities that defenders don't know. Number 3, disguising DDoS is always easier than detecting it. With the recent advances in generative adversarial learning and layer 7 attacks, smart attackers can easily imitate legitimate usage to bypass or defeat defenders. Fundamentally, as an asymmetric war, DDoS is inherently advantageous to attackers rather than defenders. Even worse, this asymmetry is magnified by adversarial machine learning and zero-day vulnerabilities. To understand it, we model intelligent DDoS as a game between attackers and defenders. In this model, both attackers and defenders are smart and strategic. The attackers aim to bypass defenders' protections by exploiting new threats and mimicking legitimate traffic. The defenders aim to accurately detect and block DDoS to maximize legitimate network service availability. Attackers and defenders mutually affect each other. They intuitively refine their strategies for their own benefits. So, in this threat model, what's the equilibrium state between the attacker and defender? Let's start from single defender's perspective and look at its optimal defense strategies. Remember that an attacker can exploit new threats and carefully crafted DDoS traffic to trick the defenders. A defender's most viable choice so far is to adopt the probabilistic filters to block DDoS traffic with the minimum hurt for legitimate traffic. So, how does this optimal filter look like? We show that for each traffic type K, such as protocol or application, the defender should forward its packets at the probability of legitimate traffic rate over total traffic rate. The defender adopts this filter for all observed traffic types. For those who are familiar with generative adversarial nets in machine learning, you will find that it's exactly the optimal discriminator between legitimate and DDoS traffic distributions. That's why it maximizes the filtering accuracy with minimal hurt for legitimate traffic. In reality, this random drop filter is easy to implement. Almost all commodities hosts and routers support it. For more details, please read the paper. Now, given the single defender's optimal filter, how should the attacker react? We consider the worst case, a brilliant, strategic attacker that can use zero-day vulnerabilities and mimic legitimate traffic. In this case, we can't assume specific attack methodologies or vulnerabilities like most threat models. Instead, we focus on a more fundamental metric, the attacker's benefit-cost ratio in launching DDoS. As an example, measurements from China Telecom show that the global DDoS becomes less frequent when the Bitcoin price increases, because more attackers will utilize their botnets to mine the Bitcoins rather than run DDoS. The recent rise of DDoS as a service on the darknet market also renders the importance of the benefit-cost ratio for criminals. Specifically, we define the attack benefit as a utility function, whose value can be affected by attack and defense strategies. This utility function can be arbitrary. The only assumption is that it gains more if more DDoS traffic reaches victims, and is zero if defenders block all DDoS traffic. On the cost side, the attacker may employ massive attack capacity from botnets, open resolvers, or self-purchased hosts for successful DDoS. To this end, we formulate the cost as attack capacity. Under this threat model, we find that a single defender's optimal filters cannot eliminate intelligent unknown DDoS. No traffic filters, including the optimal ones, can perfectly differentiate DDoS and legitimate traffic distributions. Attackers can mimic the legitimate traffic distributions to trick the filters. It's just like this puzzle war game, where the attacker strikes its DDoS traffic distribution to pass the optimal filter. As a result, even under the optimal filters, it's still possible for the attacker to guarantee an appealing lower bound of attack gains, which is achieved when the attacker fully mimics the legitimate traffic. Even worse, so far, we assume the defender can always achieve the optimal filters, which require accurate prior knowledge of legitimate traffic distribution. But in reality, the legitimate traffic distribution varies over time, which causes noises to approximate the optimal filters. In this situation, the attacker can further refine its attack strategies for higher benefit-cost ratio on the imperfect filters. Therefore, we believe we should not just passive defend DDoS after it occurs, which is not effective. Instead, defenders should also proactively demotivate attackers to launch DDoS in the first place, which is possible when the attack cost outweighs gains. This deterrence complements existing passive defenses. It bypasses all the asymmetries with a more economical, affordable solution against intelligent unknown DDoS. We designed EID, a deterrence protocol against DDoS using multi-hop traffic divergence. In real networks, traffic distributions from different nodes are naturally divergent due to heterogeneous user behaviors and network capabilities. EID uses the fact to combine weak yet divergent local defenses to form a strong global DDoS demotivation. This approach can bypass the ambiguity between DDoS and legitimate traffic. It probably knows attackers' benefit-cost ratio without knowing exploited vulnerabilities and attack strategies. It's also resilient to malicious manipulations and traffic dynamics. In the following, I'm going to show you the high-level ideas of how it works. The core of EID is a multi-hop traffic divergence. For each network node, its traffic distribution is a probabilistic distribution of traffic types plus their total data rate. The divergence quantifies the distance between two traffic distributions. It is defined as their harmonic mean in EID. The intuition is that this definition quantifies how much node 1's traffic remains after it passes node 2's optimal filters, as we have seen here. The more divergent their traffic distributions are, the less remaining traffic there will be after passing the filters. Clearly, after passing the optimal filter, the remaining traffic forms a new traffic distribution. This allows us to recursively generalize the definition from 2 to more hops, and the intuition still remains. The multi-hop traffic divergence reflects the remaining traffic when a traffic distribution passes all multi-hop filters. With traffic divergence, now think about the scenario where multi-hops enable optimal local filters as we have seen. Then, how should the attacker react? In this case, it faces the dilemma of whose traffic to mimic. Imitating one hop's traffic will lead to significant difference from other hops' traffic. This will lower the success rate of passing all filters. With this intuition, EID recursively combines weak yet divergent local filters to form a strong global DDoS demotivation. Again, think about the puzzle war game. This time, we force the attacker to strike one DDoS traffic distribution through divergent filters. It's easy to prove that with more hops or sufficiently large divergence, regardless of the vulnerabilities or attack strategies, the attacker's benefit-cost ratio will always be 0. This will demotivate most attackers to launch DDoS. Then, let's switch to the defender's view. Are they motivated to deploy EID? The answer is yes. To maximize its gain, the attacker should holistically adapt its DDoS traffic to the multi-hop traffic divergence. But from each hop's perspective, this optimal attack strategy causes significant divergence between DDoS traffic and each hop's local legitimate traffic. At the equilibrium state, this helps each defender to refine its local filter accuracy and eventually approximate 100% network service availability, as we have proved in the paper. Moreover, EID is more robust to network dynamics than single-hop defenses. Despite the temporal traffic dynamics, the multi-hop traffic divergence remains and persists. So, EID does not mandate perfect optimal filters at each hop. As long as different hops' filters are divergent, EID can always guarantee to demotivate the DDoS. In our paper, we have also discussed more practical aspects of EID, such as how to scale up EID at each hop with composable filters, how to scale out EID to large multi-hop networks with on-demand signaling-free harpooning, how to incrementally deploy EID in today's network, and how to coexist and collaborate with state-of-art DDoS defenses. If you are interested, please read our paper. We have prototyped EID in the Palo Alto Network Firewall and evaluated with a 49 terabyte real dataset from 3 hops at Tsinghua campus network. Without knowing attack strategies or exploited threats, EID demotivates both real and theoretically optimal DDoS from rational attackers. For the amplification DDoS, EID ensures its bandwidth amplification factor is always less than 1. For the direct flooding DDoS, EID ensures its profit margin is close to 0. For irrational attackers that launch DDoS without caring about the benefit-cost ratio, EID's recursive multi-hop filters can still ensure 99% network service availability under the real DDoS attacks observed from the honeypots. It also achieves 84% network service availability under the theoretically optimal DDoS strategies. All these things are achieved with only 0.5% CPU, 6 GB memory usage, and 0 signaling costs in Palo Alto network firewalls because EID reuses the random drop filters in commodity routers and hosts. In summary, in the area of intelligent attacks, we believe passive defenses are no longer sufficient. Instead, defenders should also proactively demotivate attackers to launch cyber attacks in the first place, which is possible when the attack costs outweighs the attack gains. This work showcases this feasibility in DDoS with multi-hop traffic divergence. Of course, DDoS is not the only case that deterrence works. We believe EID's core ideas can be extended to broader, intelligent, zero-day attacks. We hope in the future we can deter all cyber attacks without launching defenses. Thanks for your listening. I'm happy to answer your questions.